Hi, and welcome to ChessBuddy, a software application that allows a human to play chess against a computer over a physical chessboard without the need for the human to relay the moves played to the computer. The application also contains some optional educational functionality that allows the user to learn through digital analysis whilst maintaining over-the-board chess. Given the computer vision nature of the program, it'll be very important to delve into the board recognition techniques used, the piece recognition techniques used, as well as full demonstrations of one move being played, castling, a checkmate situation, a mathematical evaluation of a position, as well as a full game happening in real time. In the report, it is explained as to why there are two different board recognition techniques. We will now be delving into the first one. Although the aforementioned board recognition technique is extremely sophisticated, it was not chosen for the software application or the demonstration because it relies on piece detection that comes from a neural network and not just from color inference. This will be explained later on in the video. I'll demonstrate the board recognition technique that is actually utilized for the playing of a chess game. Here we have an initial frame that the computer would use to detect the chessboard. Now, we can see what the image looks like after transformation. The same Harris corner detector method is used in order to infer the inner corners of the chessboard. After that, we can infer the outer corners of the chessboard and therefore transform and crop the image into a small 8x8 grid. Notice that the image has also gone through a morphological transformation. This is in order to ensure a bird's eye view from the camera, even if the angle is 30 degrees or less than a normal bird's eye view. At this point, the program is able to hold information about each of the individual green squares and what color values they hold. This leads us straight into how the piece recognition works. From this image, the program already has the coordinates of each of the individual squares, as well as their midpoints. Every time a move is made, it checks for the largest color changes in between two squares to deduce the move that was made. This is done by measuring the average blue, green, red value of the center of each square. After every move, the color values are updated, and so each subsequent move keeps track of the color changes and allows new color changes to be made. This means that any chess move can be recognized from the user and automatically understood by the program. However, this does not involve castling, as that involves two pieces moving between four squares, or 5 squares if it's a long castle. That's why the program manually asks the user to notify it when it's going to castle short or long. This is the only move limitation that the program has. Please note that this is only a brief explanation of how the board and piece recognition techniques work, and it has been expanded much further in detail in the report. I will now be demonstrating the initial GUI launch as well as one move being played by the user. In all of the demonstrations, the user will be playing as white and the computer will be playing as black. In my physical chessboard, the white pieces are pink and the black pieces are blue. Here we can see the user launching a new game, followed by the making of a move in real time in the top left corner. After the move is made, the user clicks Confirm Move and confirms the move. As you can see, the digital representation is automatically updated in the bottom right, indicating that the move was found successfully. Now that we have seen a user move, we must now delve into computer moves. A computer move is done after a user move by clicking the Get Computer Move button. This returns, through text-to-speech, the best move prescribed by the stockfish engine at the given level. It is then up to the user to manually move the piece in the real world and click Confirm in order to update the computer's position. This will be initially demonstrated using a castling example, which will demonstrate not only the computer moves, but how castling is dealt with by the user. It should be noted that after a computer move is prescribed, the digital notation is automatically updated, even if the physical location has not been updated yet. After the user confirms the computer's move, the color values are then readjusted.
E7, E6. B8, C6. G8, F6. A7, A6.
And now I will purposely demonstrate the fool's mate that Stockfish will apply on me.
E7, E5. D8, H4. Checkmate.
I will now demonstrate how Stockfish can, through the means of text-to-speech, give the evaluation of any given position using the application.
E7, E6. G8, F6. Minus 0.15. B8, C6. $1.14.
The evaluation given of 1.14 does in fact resonate the actual position, which is basically drawn, but given that white begins the game, white has an inherent advantage which is depicted by the +1. If the advantage was in black's favor, then the text-to-speech would read a negative number. Given the difficulty in achieving a robust and scalable application, the application actually relies on code changes in order to adapt to a new environment. Because of this, I am open to any future demonstrations. Ideally, I would have implemented an initial GUI that allows the user to focus their camera pick their camera source as well as adjust the camera position in order to determine the position of the board. Thank you for watching, and I hope you enjoyed ChessBuddy.